We're going to be beginning chapter 13, our discussion of chemical kinetics. So there are two major driving forces that will drive the outcome of a chemical reaction. And the one we discuss first is kinetics, and then the one we'll be discussing after that is thermodynamics. All right, so let's go ahead and begin our discussion of chemical kinetics today. And whenever you hear the term kinetics in chemistry, we can go ahead and drop the chemical term from now on. We're just going to call it kinetics. That's what everybody else does. Kinetics, you have to get this in your brain, is going to be the rate of a reaction. And we say the rate is fast or slow. Right? And that's how we define kinetics. Okay, thermodynamics is going to be completely different. Thermodynamics we'll discuss next. It's nothing to do with how fast or slow a reaction goes. That is all about kinetics. All right? So whether something is fast or slow is something you've had quite a bit of experience with in everyday life. But we're going to go ahead and define that mathematically. We say the rate of anything is going to be, well, let's just say the rate of driving in a car, for example. That's going to be the change in distance over the change in time. And we can abbreviate that, delta x, all right? So this would be a change in position or distance on, let's say, the x-axis, or from one point of the street to the other point of the street. All right, so we'll say that's the change in x, or change in position, and then we have delta t. So that's how we can define rate. All right, so if you were thinking about how your car is measured, the change in distance would be the change in the miles and the change per hour. So they have miles per hour. Or in physics, the standard unit there would be meters per second. All right, but what about for chemical reactions? All right, so for chemical reactions, we don't measure a distance. The most convenient way to measure the progress of a reaction, if you will, is going to be the concentration. So the rate in chemistry, we're going to look at the change in concentration of some compound A. All right, and these square brackets, just to review, are brackets that indicate molar concentration of A. All right, and of course the delta means change. All right, so then we have delta T for time. So the change in concentration of A is per unit time. All right, so why don't we go ahead and just make a fictitious chemical reaction here, where we have reactant A being converted into product P. All right, so we can look at some time points of this chemical reaction. At time 0, all right, so I've got my little t and then the 0. That means at the very, very beginning of the reaction, my concentration of A is given by A naught or A 0 or A initial. All right, these are initial concentrations of A. So you just have that sitting in your container or your vessel, and that's what it is. All right, and as time marches on, we have time t. All right, that's just some time that's greater than 0. All right, at time t, the concentration of A will have changed to AT. So this is some concentration of A after time t. Now, let's look back at the chemical reaction here. A is being consumed to be forming P. So that means over time, our concentration of A should be going down. It's being consumed, all right? So what we can do is write a mathematical relationship there, saying that the initial concentration of A will be, oops, not that way, will be greater than the initial concentration at time t. So that means the initial concentration is going to be the high point, all right? But let's talk about time zero for P. Time zero for P, P0, whether you start with it in there or not, is going to be the initial concentration. If you have no P at the beginning of the reaction, then P0 is equal to 0. After time T, the concentration of product P will have increased to PT. All right? So it's a bit different because the product is being produced over time. So we expect to see a greater amount of product as time moves on. All right? So they have a different relationship. A naught or A0 is going to be higher than AT, and P0 is going to be less than PT. And what we can actually do is graph this relationship of A going to P. And we're going to look at a lot of these plots, right? They're very helpful to visualize what's going on. And I'm going to put T here, and then we're going to have concentration on the y-axis. All right, so concentration of which one? Well, it doesn't matter right now. So what's going to happen is we're going to see something like this for the concentration of A, all right? And then we'll see the mirror image there for the concentration of P, all right? So what this is showing us is that as we have A being consumed, its concentration goes down, and as we have P being produced, its concentration goes up, all right? So what we can do is we can say that the rate of delta A, the change in A, and the change in time, all right? And we need to put a negative sign there, okay? And the reason we need to put a negative sign there is because A is being consumed. So what that means is the change in A is going to be a negative number, and we can't have a negative rate, right? You don't have a negative 5 miles an hour. So in order to change that negative rate, what we're going to do is have a negative sign. So a rule of thumb, the rate for any reactant is going to need a negative sign out in front of it, all right? We can equate this rate to the production of P, all right? P is being produced, so we don't need the negative sign there, all right, because we're going to have a positive rate of formation of P, all right? So this is our general rate equation forms, all right? So the rate of any reactant is going to be negative delta concentration of that reactant, in this case that reactant is A, over its change in time, and it's going to be equal to delta P over delta T, and we don't need the negative sign there for the products because they're being produced. All right, let's take a look at a real chemical reaction for a moment. Let's take a look at hydrogen gas reacting with chlorine gas. And this is going to produce 2 moles of hydrogen chloride gas. All right? So can we write rate equations for each reagent? When I mean reagent, I mean products and reactants. All right? So let's do the H2 first. Okay, so H2 gas, that is being consumed, correct? That being a reactant means we need that negative sign to correct for the rate being negative. So again, anything being consumed needs that negative sign. So it's going to be delta hydrogen over delta chlorine. All right? It's also going to be equal to negative delta chlorine. Oh my gosh. I'm so sorry. I don't know where I'm going with this. This should not have been delta chlorine. It should have been delta T. I was jumping ahead to the chlorine already, right? Rate is always change in reagent divided by delta T. And in this case, that is a reactant. So we need this negative sign here. All right. Apologize for that. Okay. Now we can do chlorine. Okay. So there we have our expressions for both of the reactants. Now, for the product, something's a bit different here. There's a coefficient of 2. All right. Notice these guys had understood coefficients of 1. Okay. Fine. So what are we going to do with these coefficients? So let's just draw a picture of what's happening here. If we looked at hydrogen gas here and chlorine gas here, right? Those are what we call diatomic molecules or binary particles. And what happens is that they react to make 2 moles of HCl. All right. So let's go ahead and put an artificial rate here. Let's say that the rate of consumption of the H2 is 100 particles per second. Okay, and by definition, what will the rate of consumption of the chlorine be? 100 particles per second. All right. So if H2 and Cl2 are both being consumed by what we just made up a rate of 100 particles per second, that means that this guy is going to be produced at 100 particles per second. Okay, this one must also be produced at 100 particles per second. So in the end of the day, H2 is being consumed 100 particles per second, Cl2 100 particles per second, and then each HCl molecule is being produced at 100 particles per second. But if you add that together, that's 200 particles per second, and that's twice the rate of the other guys. So we're not actually producing it at twice the rate. It's just that we're making 2 separate molecules at 100 particles per second. So how do we address that? Well, we need to cut that number in half. So the rate of production for the HCl now it's production, so we don't need a negative sign, but we do need to cut it in half. So it's 1/2, all right? Because we're actually just producing it at 100 particles per second, but it's just 2 separate molecules being produced at that rate. Okay, so general form of a rate equation, we can finally do that. Let's say we take A plus B goes to C, all right? And I want to point out that the lowercase letter is the coefficient, and the uppercase letter is the chemical. Okay? So much like we had H2, all right, the chemical would be H2 and the coefficient would be 1. There we had the chemical, which is HCl, and the coefficient there is 2, all right? So this would be the lowercase letter, and this would be the uppercase letter. Let's put this all together now. We have 1/A, all right? That's 1 over the coefficient for A. However, since A is a reactant, it's going to be consumed. All right? That is how you'd express the rate of reaction with respect to A. All right? Now, the rate is going to be equal for everybody. All right? So the rate of reaction is going to be the same number for B. It's just going to be a different expression. So what I can do is go ahead and delete rate for now and try to express this in terms of B. B is a reactant, so it will be consumed, and we have delta B over delta T. All right, so that lowercase b addresses the coefficient problem we could have. All right, and finally we can equate this to C, and C is a product. All right, so it is not being consumed, it's being produced. So we're going to have a positive sign out in front. Okay, so we have 1 over C, delta C over delta T. And all three of these are equivalent to the rate. All right, so that is the general expression for a rate equation. All right. So let's go ahead and work an example here with some real chemicals and numbers. So I'm going to look at this monster equation here and show you that it's not that bad no matter how big the equation gets. All right, so I'm going to take some aqueous hydrogen peroxide and I'm going to mix it with iodide and a little bit of acid. And that's going to give me this I3 molecule and water. All right, so I put the phase labels on there. AQ, of course, is aqueous and L is liquid. All right, so in the first 10 seconds of the reaction, concentration of iodide, I minus, dropped from 1.000 molar to 0.868 molar. Calculate the average rate of reaction in this period. All right, so we're given a few numbers here. We've got time, going to be 10 seconds, all right? And then we're given some concentrations here. So we have a concentration of iodine and time. So let's go ahead to the next slide and put together what we've got, all right? So we've got an initial concentration of I minus. So the way I'm going to write that is I'm going to say this is I0, and that initial concentration was 1.000 molar. We have a final concentration of iodine, and the way we can write that is it is at time t. All right. So at time t, it fell to 0.868 molar. All right. And our time was 10 seconds. All right. So it's easy to say that our initial time was 0 and our final time t was 10 seconds. So what we can say is our delta t is equal to 10 seconds. All right, that's how long our time was measured in this chemical reaction. All right, so we have delta t, and we can also get delta I minus here. And what that's going to be is it's going to be the change is always the final minus the initial. So in this case, it's going to be the time, or sorry, the concentration of I minus at time t minus that initial concentration. All right, and let me move this over here. And that change in time is 0.868 seconds minus 1.000 seconds. All right, so we subtract those, and subtracting those numbers gives me a number of negative 0.132 molar. Oh goodness, I called them seconds up there. These should be molar. All right, so 0.868 molar minus 1 molar gives me negative 0.132 molar. So now I've got my delta for concentration and my delta for time. All right, so all I need to do now is write the general rate expression for the iodine. So the rate is equal to, let's go back and look at the stoichiometry of the chemical equation. So I minus right here has a coefficient of 3 in front of it, and it's also a reactant, so it needs that negative sign. Okay, so my negative sign right there, and it had a coefficient of 3, so I need to correct it. So 1 over 3, and then it's going to be delta I minus over delta T. All right, and I can plug those two numbers in, so it's negative 1/3 times negative 0.132 over 10. All right, so this is molar per second. And I'm going to do that. I get negative, oh, sorry, the negatives cancel. So plugging all that in, I get a rate of 0.0044 molar per second. All right. So that is how you would calculate the change, or sorry, the rate for any chemical reaction given those numbers. All right. Okay, now we need to look at something a little bit different in chemical kinetics, and we're going to talk about something called the rate law. So the rate law is a mathematical expression that takes into account the effect of concentration on the rate of reaction. All right. So let's think about this for a moment. What this is saying is that the rate of reaction is affected by concentration. All right. We kind of saw that earlier where, yeah, you had a final minus initial. But what we're looking at here is how the concentration is going to change. And as the concentration is changing, the rate will also be changing, right, for most chemical reactions. There's one exception that we'll get into. All right. And the reason that is we think about something called the kinetic theory, all right, in chemistry. As you consume more and more of the reactants, there's less of them to react, all right, and there's less of them to find each other, if you will, to react, so that reaction rate's going to go down, all right. So the way we can kind of paraphrase that is that rates of reactions will decrease as the concentration of reactant decreases. One major exception we'll get into later is something called the zero order reaction, but when we talk about orders of reaction, we'll get into that. All right. So again, to think about this, if you have A plus B going to C, as you consume A and B, there's less of them to collide with each other, and then it's going to take longer for them to find each other, to collide, to make product C, or combine, if you will. So the reaction rate's going to go down. So what we could do here is look at this plot. If we look at the concentration of A over time, all right, what's going to happen is at the very beginning of the reaction, A is going to find a lot of B, right? And the reason why is because at the very beginning of the reaction, see we're down here at time 0, there's a lot of A, all right? And there's very little C yet. So A has a lot of opportunity to react because there's a lot of it. So it's going to consume itself very quickly, all right? So it's going to have a steep slope downward, all right? But as it starts consuming itself, there's less of it around to react, and then it eventually just kind of plateaus, all right? So what's happening here is we have a very rapid rate of consumption at the beginning of the reaction, and then it kind of slows way down, all right? So this is what your typical plots for the concentration of A versus T is going to look like for chemical reactions, all right? So what we need to do now is talk about reaction order. And this is really going to tell us what kind of rate law we have, and it's going to tell us the sensitivity to concentration change. So how steep is that slope at the beginning, right, is what this is going to measure. So what we're going to have is a rule of thumb saying that the higher the reaction order, the more steep that initial slope is, and how much more sensitive it is to concentration change. All right. So what we're going to do is look at 3 of these, and we're going to take them in order here. We're going to look at what we call first order. We're going to study second order. And finally, something that we call zero order. And this is the funky guy that is not sensitive to concentration change, all right? So there's zero order, not sensitive to concentration change, first order and second order, right, that are going to be sensitive to concentration change, all right? And these can be abbreviated as zeroth, all right, order, second order, and then first order, all right? So you've certainly heard of first and second as abbreviations, but zeroth might be a new one for you. All right, but that's it. All right. So why don't we look at the first order reaction first? All right. This reaction is indeed sensitive to the concentration change. All right. So the way this is going to work is we're going to have our rate law, and we're going to express it. We need a chemical reaction first. Let's just do A to P, right? So A going to P. And we like to always express our rate laws in terms of reactants, all right? So what it's going to look like is going to be rate is equal to lowercase k, I'll explain what that is here in a second, times the concentration of A. And there's going to be an exponent here in all rate laws. Here it's going to be 1 for first order. Of course, we know you do not need to put an exponent of 1 on anything, all right? So if it's left blank, you assume it's 1, all right? So let's look at this lowercase k, all right? Now make it funky cursive k because I don't want to confuse it with uppercase k, which is our equilibrium constant that we deal with a lot in thermodynamics, okay? So K is something called the rate constant. and it's specific for a particular reaction at a particular temperature. Right? So the rate constant is temperature dependent, all right? And it's going to change depending on what kind of chemical reaction we have. But the idea is that a rate constant that is large indicates that we're going to have a fast rate or a high rate, and a rate constant that is relatively small is going to be a relatively slow reaction. All right? So the next one we want to look at is something called a second order reaction. So a second order reaction happens to be more sensitive, all right? And its rate law looks like so. And this is going from A to P as well. So maybe asking, well, how can you tell whether a reaction is going to be first order, second order, zero, or whatever by just looking at A going to P? And the answer is you cannot. All right, we have to do experiments to figure out what the order of the reaction is. So let me go ahead and make this clear. You cannot tell what the order of reaction is by just simply looking at the chemical equation, all right? And in fact, there are many more orders of reaction. There are half-order reactions, 3/4 order, 4/3 order, 5/2 order, all kind of wacky order reactions. But we're just scratching the surface here and only going to be talking about first, second, and zeroth, all right? And you cannot look at the chemical equation to figure out what they are. We have to do experiments to figure out what order they are, all right? So back to this. This is a second order reaction, all right? That exponent of 2 tells me that it is second order in A. All right, let's go back to this slide. Looking at this rate law, it is first order in A. All right? Here you'd say it is second order in A. Now, because we have an exponent of 2 there, the reaction is going to be much more sensitive to the concentration of A, because whatever you put A there, it's getting squared, all right? So that whenever you square a number, you're increasing the sensitivity of the rate, all right? Whereas in the first order reaction, it's going to be less sensitive because you don't have any exponents there. All right, we can make it a little more complicated. Why don't we say we've got A plus B going to P. Now we have 2 components, or 2 reactants. So what if I gave you a rate law like so? Okay, go ahead and ask the question, order in A. So just look at the exponent. Easy as that, okay? So from the rate law, you can really quickly tell me what order reaction is. Okay, order in A is first. Order in B, also first. Order overall, well, first and first, or more accurately, you add the exponents, all right? 1 plus 1 is 2, so overall, that exponent sum is what? Second, okay? So as we progress in our studies of kinetics, the overall order will make more sense in a little while, but we need to be able to identify the orders of these reactions, okay? So it's first in A, first in B, second overall. All right. What if we had another one where the rate law came out to be this? All right. So I've got an exponent of 2 here and an exponent of 0 there. Okay. So what is it in A? What kind of syntax? Okay, so order in A. Second. Order in B. Well, that's an exponent of 0 now. All right, so it would be what? 0th order in B. Overall order. 2 plus 0 is 2, so we get second. All right, so that's second overall. Okay, so we have our ways of telling whether it is going to be second, 0th first order in A, B, C, whatever it is, or if overall we just need to add the exponents. So whatever the exponents add up to, that's the overall order of the reaction. Okay, and just to clarify, we cannot tell what kind of reaction order, or sorry, what kind of rate law we have without experimentation. All right, and what I want to do in the next video is talk about that experimentation, and it's going to be done by something called the method of initial rates. All right, so look for that in the next video. Thank you very much.